Hi, I'm Mr. Richmond. This is your Integrated Math 2, Unit 12.1, Lesson Summary. Now in Unit 12, we are finally moving out of the realm of geometry in our math course and back into the realm of algebra. And so some of these algebra skills from Math 1 are going to have to start hitting again. We're going to be focusing on solving equations, graphing equations, using tables, writing functions, looking at input-output, x-intercepts, y-intercepts, etc. So there's a lot of topics here that we're going to hit again. Feel free to use the Integrated Math 1 videos. The first semester would be a better bet, chapters like 1 through 7. Reviewing those videos may help you kind of get comfortable with algebra again as we move into chapter 12. With that said though, let's talk about what we'll be doing here in chapter 12. So we're now going to focus on quadratic functions. And you did learn these in Math 1 briefly. You didn't do a whole lot with them. But quadratic functions are any function where your variable x has a squared term. So if you have x squared, or even just x squared and x, something like that, is now a quadratic function. So just to kind of show you, you can see them with y, like this would be a quadratic function. This here could be a quadratic function. You can also have them in function notation. And there's a lot of variability in how these look. The biggest key being it needs to have at least an x squared term. It could then have lower powers as well, and it's still a quadratic function. And the graph of all these look the same. They create a U-type shape, which we call a parabola. So these are examples of what any quadratic function will look like if the leading or the highest coefficient you have, or sorry, the highest degree you have is 2, if it's a x squared term. And so one of the forms we're going to learn about is standard form. Standard form of a quadratic function will look like this, and this time now it's in function notation, f of x, rather than our basic equation form of y. This is the same though. Whatever stuff you would do typically in math with y, you can still be done with function f of x. It just gives us a little more information about what exactly our input is in the problem. Okay? And in a typical quadratic, you're going to have coefficients here in front of the x squared term. Could be 2x squared, 3x squared. It can even be just a negative 1x squared. This first term that's in front of your x squared is considered the a value, 2, 3, or negative 1. And that's going to tell us some things about the quadratic. And you'll learn about this more in the next section, but it's going to determine whether it opens up or down, etc. B of x is going to be affecting the shifting of it, kind of in a left-right, but with this it does actually move more in a parabolic type shape. And C is always going to represent our y-intercept, or the starting point on our y-axis for our graph. And all this we're going to learn more about in the next section. This first section is more about investigating quadratics and starting an idea as to their properties. So we won't worry about that too much right now. Two of the terms you are going to look at though are a term called the absolute maximum and the absolute minimum. The absolute maximum of a parabola or a quadratic is the coordinate that yields the maximum value for y in the quadratic function. It's basically the highest point this graph ever goes to. That's your maximum. Your minimum will be the lowest value it ever goes to. And so when you have a parabola and it makes this U shape, it goes on forever, potentially both sides going up forever. That means there's a lowest point that it ever curves to. That lowest point would be the minimum. If the parabola is reflected and going downwards now, instead it's going down forever to the left, down forever to the right, so there's a maximum value that it touches. The highest level is a maximum. All parabolas, all quadratics have either a maximum or a minimum, but never both. Okay? It's going to have one or the other. Once you know what direction it opens, you're able to determine that, and we'll talk about that in another section. So for now, what I'm going to do is just kind of get into a word problem to show you how certain things in the real world create quadratic functions and give you an idea, talk about the difference between an expression and a function, and actually start to write one. Okay? So here's my example problem for today's lesson. It says, you are building a rectangular garden in your backyard with 2 equal square sections on each end for storing materials. So I'm going to try to draw a picture of that so it helps understand it. But basically we have this rectangular portion, and let's kind of imagine this is like dirt or plots or whatever. This is your garden. This is where you're actually planting all your plants. And then on each side is a square section for storage. And this might be where you store your seeds, your mowers, your clippers, or whatever tools you need. And so that's basically what your backyard garden is going to look like. Okay, it says the length of the rectangular portion of the garden can be no more than 30 feet. So this entire thing here has to be 30 feet. And it says let X represent the width of each square storage section. So squares we know are, equilateral. They have all sides equal. So if the sides of the square has to be X, then I know that these sides here are my variable X. And basically what's going to happen is this. Let's kind of think about it. If I wanted this garden to be 28 feet, then that means this is only 1 foot and 1 foot. And that would be the best I can do, because I only have 30 feet to work with this way. So if I go 28 here, then I'm going 1 foot, that adds up to 30. Or I could go 24 feet here, and that gives me 6 more feet to work with, so I can go 3 and 3. Okay, and what that does is it kind of either elongates my garden, right, if I did almost all of it this way, or I could go shorter this way and allow it to be longer this way. So it's just kind of showing you all the different kind of rectangular shapes you can end up making here. And what we're going to eventually get through this problem, let's kind of look ahead at what it's saying and then we'll go back. But it says write an expression for the length of the rectangle and an expression for the area of the rectangle. So that must mean just the rectangular garden portion here. And then write a function for the area of it in standard form, and then determine the absolute maximum or minimum. So if I'm making this garden, right, and I want to maximize, this is what I have to work at, I want to put as much stuff in the space as I can, so I want to maximize the space. I don't want to create these humongous storage containers that then I don't have any garden space. So we're going to start to look at how this relationship works by creating a quadratic function. So let's start with this. Keywords, things that drive math teachers crazy. Is when students don't know the difference between an expression and an equation, or an expression and a function. Okay, huge difference. Okay, an expression has variables, has numbers, has operations, add, subtract, multiply, divide, but doesn't have an equal sign. It's not an equation. It's something like this. What's the cost of potatoes? $4 per pound. That's an expression, 4p. What do you get paid an hour? What's your hourly rate? $7.50 per hour. So that's my rate. As soon as I say, write a function for the cost of potatoes. Okay, the cost of potatoes equals $4 per potato, or per pound. Now it's turned into an equation, and any equation can also be a function by just simply changing the notation. So if it says equation, you should have 2 variables, an input and output, and an equal sign. If it's an expression, you don't need that. They just want the variable expression. Okay, so that's huge. If you know that difference, your math teacher's going to like you a little bit more. Okay, keep that in mind. So write an expression for the length of the rectangle. Tricky. The length of the rectangle would be this portion here. Now, what would it be? Well, if I have 30 feet to work with, x has to go here, x has to go here. 2x of it is gone. I don't get to use it. So this really can only be whatever 30 minus 2x is. So my expression for the length has to be 30 minus 2x, because that's all I have to work with. If I make x 5, then this x has to be 5. I've now used 10 feet. So 30 minus 10 means I only have 20 feet left. And this part can be hard. It can be kind of difficult writing this expression and thinking this way. So try with different numbers. Once you write something, try different x's and make sure it makes sense. Mine makes sense now, so I'm going to run with it. Now I need an expression for the area of the rectangular garden portion. Okay, an expression for the area. Well, the area of a rectangle is base times height, or length times width. My length is 30 minus 2x. My height, no matter what, is going to be x, because if I change it here, it changes there. The height is just x. So my area would be x, the height, times 30 minus 2x. I just added the area formula. Okay? So now I've written expressions. Okay, and I mean, you know what? I didn't want there to be confusion, because equal sign might make you think that this is an equation, so I'll just do that. An expression, has variables, has numbers, has operations, no equal sign. One variable. Okay? Writing a function now, would be like y equals these. Y equals this. The area equals this. You can even see area, A. So let me write an equation first so you get it. The area equals x times 30 minus 2x. That would be an equation for this. Okay? They want me to write a function. A function just changes slightly. The only difference is instead of the left side being just A or whatever, it's the area depending on what you plug in. And what I would be plugging in are values of x. So the area with input x equals this. And it's interchangeable. What does my area depend on? Well, it depends on x. What is x? X is actually the width of the square or the rectangle. You could even change that to a w if you wanted and say the area depends on w. Okay, it's interchangeable as long as they match. That's really all it's saying. It's saying what you're plugging things in for. Okay? Now, here it said let x represent the width for this particular problem. So I do want to stick to the variable that they told me. But if it doesn't give me a variable and I'm choosing, you can make it whatever you like. Whatever your little heart desires. Okay? However, it says write this function in standard form. And standard form is supposed to look like this for a quadratic. So what I need to do is undo parentheses. There's no parentheses in standard form, so I'm going to distribute and rewrite it. So my area as a function of x must equal x times 30 is 30x minus 2 times x is 2x squared. And according to my standard form, x squared is supposed to go first. So I'll actually rewrite it one more time in the correct order and say negative 2x squared plus 30x. And there's my function for this, for the area in terms of x. And now I can get the area for anything you tell me. So if you said, I want to make this 5, what's the area of this rectangle? Okay, well I plug it in here, 5 and 5 makes 10, leaving this to be 20. So it's 20 times 5. 20 times 5 is 100, so the area would be 100. Or, since I've done the math ahead of time, the algebra ahead of time, I can just use this new formula. Plug in 5 here. 5 squared is 25. 25 times 2 is negative 50. 5 times 30 is 150. 150 minus 50, 100. And I can get the area that way. And so this also, now that it's an actual function and not just a visual, allows me to graph it. And I can actually show every single possible answer. And I can watch how the area changes as I plug different x's in. And that's what I'm going to do now, because I want to find what the maximum area is. The only way to do that would be to make every possible dimension here for x, and that's a lot of work. But if I can look at a graph that shows all of them at one time, I can get this answer quick. And now I am in the next section going to show you how to do this without a graph. But for now, let's just graph this on our calculator and see what it looks like. So I'm going to go to my graphing calculator. I'm going to go to the y equals menu. I'm going to make sure that plot 1 is not highlighted. I don't want anything in there. I'm going to type in the equation, negative 2x squared. Oops. Negative 2x squared. And then plus 30x. And I'm going to hit graph. Now I'm going to pull this over to you so you can see. Hopefully I can get that steady. Now one thing I want to point out here is when I type the squared, it's going to put you up in the exponent. You have to then press the right arrow to get out of there so that you're back typing on a normal plane. Then I hit my graph button. Okay, and what's likely going to be the case is your window does not match your problem. So we have to start thinking about domain and range in Windows. So you can do a little trick here called zoom fit. If you press the zoom button and then scroll all the way down to 9, it sometimes gives you a kind of a recommended window for it and allows you to see it. But now you can see I don't see the whole parabola, and that's the only problem with that zoom fit is it might not give you exactly what you want. So I'm going to think about my window instead. I'm going to press the window button and see what they did. So they did a Y max of 112, and that was high enough, but I'm going to go a little bit higher so I can see all of it. But the X max, the left and right, didn't go far enough. So I'm going to go a little farther and make it 20 and see if I can see more of the graph. And now I can. And so this is showing you the area for different values. And so I can press a trace button and basically my cursor follows along and shows all the different answers for x. So if you made x 0.21, what's that? So if you press the trace button down here, it puts a cursor on there that you can then follow the graph and see all the different answers. So watch my x there, it's almost at 2. So if I make the x 2 in this problem, my area would be 50. And I can kind of follow it, and my area is climbing, 110, 111, 112, 112, 111, 110. So I've passed the maximum point of the parabola, and I'm now kind of working back. So there's definitely a spot here that you want x to be that creates a maximum. And there's a function on the calculator that calculates it for you, so you don't have to estimate it. And it's second trace. So if you press second trace and scroll down to where it says maximum or minimum, this one is a maximum because it's at the height. So I choose maximum. It's going to say left bound. And so I just want you to choose a point that's on the left side of the maximum. And you can kind of visually see the max. So as long as you don't go past it, it doesn't really matter how far left you are. Press enter once, then scroll right past that maximum so that you're kind of trapping it in between your two bounds. Press enter for the right bound, then it'll say guess. You press enter again, and it's going to guess our maximum. It says 7.5, and then round it out 0.00031, so I'm going to say around 7.5 with a max area of 112.5. So my max is at 7.5, 112.5. And what's important is that you can determine what that max means in terms of the problem. Well, what's it mean in terms of the problem is if the width is 7.5, and I think we're in feet, so if I make the width of the actual structure here, the 7.5 and 7.5, then I will have a max area for the garden of 112.5 feet. And so for now, and probably in your homework, the first homework, if you have a graphing tool, you can just graph your equation when it's in standard form and use the maximum feature to find it. But there is a way to find this algebraically without actually touching the calculator or seeing the, without seeing the graph, and we'll learn that in a future lesson. So hopefully that helps you out. Good luck.